Last week we started vibrations and waves. And we're going to make more waves today. Friendly reminder review here, some terminology. What's the difference between a vibration and a wave? Good. Which is that? Yeah. A wave is a wiggle in space. Remember the vibration was like the laser, the UV pen, laser pointer? That's just vibrating back and forth. That's like a wiggle in time. But as it propagates through space, or space moves by it, you get a wave. And this is a pictorial representation of a wave. Vibration in time and space. So with time it goes up and down, but in space it moves this way, covers a certain distance. What do we call this? Amplitude, good. What do we call this? Amplitude. It's the maximum displacement away from the, what's this line? Equilibrium position. Good. So for a pendulum, we'd say this spot's equilibrium. And if I displace it to here, here, and here, the distance to the equilibrium is the amplitude. So this distance or this distance, the maximum distance it gets away from that. What's this called? Right, wavelength. And that's the distance the wave travels in one cycle. Because it starts down here at the bottom, and by the time it gets to that same point in the cycle, it's over here, propagated through space. What do we call the bumps on the bottom? Trough. And the top? What's the period tell us? Time, good. It's a time. How long? What's it describe? Yes, time for one wavelength. That would be the time it takes to go from here to there. One cycle. Yeah, time of one cycle. One wavelength. One period. Frequency? Rate of vibration. And how do these two compare? Yeah, they're inversely proportional. This one's in seconds. This one's in inverse seconds. 1 over seconds. 1 cycle per second. Tells you the rate that it vibrates once. That tells you the time, the actual time it takes to vibrate once. What's the unit for frequencies? Yeah, that was cycles per second when you forget what a hertz is. But that, yeah, that's a hertz. Not a hertz donut, that dumb joke, but you know. Okay. Good. Oh, yeah. And so vibration, emphasize again, because I asked a question at the very end last time, a clicker question. This motion is the vibration, and that would give the amplitude. This motion gives the wavelength through space. The medium vibrates. Like these individual rods, we'll leave it there. They move up and down. One of these, it comes and it just moves up and down. It vibrates in time. The wave seems to propagate space. The disturbance or the pulse, whichever helps you remember it, that you can see. It looks like it's traveling. That's the wave. And that has a certain speed. It's not how fast this thing's going up and down. It's how fast the pulse or the disturbance seems to be traveling. That's the wave speed. V. And what does it equal? Yeah, you're both right. That. And if you forget, because sometimes I do, I did this before. Way back, our very first unit with motion, what is velocity? It's the rate at which you're changing distance as you move. So many miles per hour, a distance per time. Distance per time. What's the distance of a wave? It travels one wavelength. In what amount of time? One period. You can write it like that too. Distance per time. How far one cycle travels, and that's how long it took. Yes?
This might just be me looking at that, but it looks like for wavelength time is uppercase E, whereas phase it's lowercase, usually case matter.
Yeah, one of those where they got so many letters to pick from. Before, time in general is lowercase t, like we had earlier in the semester.
Yeah.
For a period, we use uppercase t because it's specific for the time of one cycle. So it's meant to be uppercase. Thank you. So I'm just making the connection here, distance over time. And you can rewrite that. 1 over the period is the frequency. So that's generally how they write it. But they all give you the same answer. And there'll be questions on your homework and probably the exam where sometimes it's better to think like this. Well, it covered that much distance in this much time. You'll get the same wave speed as if you figured out the wavelength and the period. It's all consistent. And we're going to play around more this week. How as some of these change, the other one must change, because this is our equation to guide our thinking. Yeah, there's our review. I didn't think I covered it well enough. A pendulum. Your book talks about it. We talked about how mass didn't matter on a pendulum. Didn't affect period. So these two different masses, if I let go at the same time, swing together. So that tells us they have the same period and the same frequency. You are getting sleepy. So mass doesn't matter. And the connection I was trying to make, I want to do it again, is remember when we dropped balls? They'd fall at the same what? Time, yes, and rate. And we call that rate the acceleration due to gravity. Yeah, they accelerate at the same rate, so they take the same amount of time to go down. And I mentioned it, but it was too quick. Which object, here, something heavy, something light, which one is being pulled with more force to the ground? Yeah, the heavy one. Because inertia, Newton's second law, F equals ma. F equals ma. The one with more mass has more inertia, so it'll resist that change. So you have to exert a larger force on it to acquire the same acceleration, which is why they accelerate together. And that works dropping on an incline or pendula, because it's gravity that's trying to accelerate them down. That's why mass doesn't matter for a pendulum. What did matter? We did that. The length does. So again, you can shorten it, and now it's faster. Let's compare, because maybe none of you have done this. Let's find out. Let's find out the period of this guy, the rubber lighter ball. I'll swing it. Actually, let's swing it little. Okay, so I'm going to start when it's right here in its cycle, on this side, here, here. And I'm going to time, go. Okay, there's 1 oscillation, 2, 3, 4, 5. I'll do that. That's long enough. So we had 5 cycles in, I'll round up, 10 seconds. So that is that going to give us the period or frequency? Good. That's the frequency of 0.5 hertz. That make sense? Let's compare. If I make a bigger amplitude, do you think it'll be more or less? One cycle, 2 cycle, 3 cycle, 4 cycle, 5. Well, what do you know? It's still 10 seconds. So amplitude doesn't affect it either. But as we saw, let's do this one. Length will. Clear that. Go. 1 cycle, 2, 3, 4, 5. So that one was 7 seconds. I don't know what that is in decimal, but it's faster. The period of this would be what? 2, right, 2 seconds. It takes 2 seconds to go back and forth once. And this period, 7/5 of a second. A little over a second, but less than 2 seconds. So it's faster. Your book gave a formula, and I'll write it up again. It was kind of in the bottom in the footnote. For a pendulum. That's exactly it. What I want you to know is the period is proportional or depends on the length. If you make it longer, it takes more time to swing. And if you increase the acceleration on it, this would be a bigger number, and make the period a smaller number. It would swing faster. But it has nothing to do with amplitude or mass. So when you swing with your kid, you jump onto the swing with them, it shouldn't change your period. You could check that. But what if you stand up in a swing? You've just kind of effectively shortened the pendulum. Instead of all your weight being down here on the swing, if you stand up, it's like a shorter pendulum. You should swing a little faster next time you're playing on the playground. Something different are masses on springs. Let's do this guy. Here, this we'd call the equilibrium position, because that's where it wants to, it's not moving, wants to stay at rest. If I displace it by exerting a force on it, it oscillates. It's now vibrating in time. This would be the amplitude, the maximum displacement up, as well as down. And can you see it vibrates? Let's figure out what that one is. Now, 1, 2, 3, 4, 5. That took 5 cycles in 5 seconds. So the frequency is 1 hertz, period 1 second. If I increase the mass on this, do you think it will matter? Go. 1, 2, 3, 4, 5. That took 7 seconds. It is slower. The mass does affect when something physical is trying to vibrate it. The force pushing and pulling this mass is the spring. And the spring is only so strong. So if you increase the mass and the inertia, it's going to resist this force more. It's not accelerated as great as it was with a less mass. But that's because the springs are trying to exert the force. Everything I just discussed before had to do with gravity. And we learned it makes the acceleration the same. That's why mass doesn't matter for them. But with a lot of things that are trying to vibrate, like this, or this, the wave machine, a guitar string, drum heads, if you increase the mass by having a fatter, thicker string, or putting blobs of clay on here, then it's going to resist that force more, and it'll vibrate more slowly. Does that make sense? That'll come into play more in a couple chapters. But with the instruments, as you look around, if the mass increases, generally, that means it's more sluggish. It's going to resist you more and vibrate more slowly. Yes?
Is the mass really the factor or the reason because the spring got wider or longer?
Yeah. The idea there, the fact that it got longer, should be a clue to you that this is the force trying to stretch it. It stretches that far. Because which two forces are balanced right now? The weight of the block and the upward pull of the spring. They must be balanced. More mass. We have two forces that are balanced again, but this force is larger, isn't it? It's heavier. That's a bigger force down. So the spring has to pull back more, but that makes it stretch further. Does that help? And so, yeah, it's a little more sluggish. You can change the spring, too. This has to do more with instruments. Let me do this spring. It's stiffer. It's tighter. Like, what happens in a guitar when you make the string tighter? Higher pitch. Does that mean it's vibrating faster or slower? Faster. So this is like making a tighter string. So let's see. Oh, yeah. It's a little zippier. Same idea. This spring is stronger. There's more tension in it, like with a guitar string. So you can change frequency on most instruments and things by adjusting the mass or the tension. Some people get confused between these two because this one didn't seem to matter with mass and this one does. And that's why I'm trying to clarify here for you. You good so far? Okay. Groovy. All right. So there's two types of waves, characteristics. There's many kinds of waves, but we describe them. They basically all act in two different ways. One we call transverse. Transverse. And that's like this. You make a vibration, and the disturbance, the medium, the rods, vibrate vertically, up and down. But which ways the waves seem to be going? Side to side, left to right, horizontal. So if the vibration is perpendicular with the wave, we call it a transverse wave. So I like to say, perpendicular. Right angles. The other kind is called a longitudinal wave. And it's more like a slinky. If I make a vibration in the slinky, it makes the individual coils go side to side, left to right. It's hard to talk over that, so I'll stop. Which way does the wave or pulse look like it's going? Left to right. So they're parallel. They're in the same line. The individual coils, though, they compress and then they spread out. They compress and spread out. See right in the middle? That's longitudinal. So I say they're parallel. The vibrations and the waves are in the same axis, along the same line, same direction. Some examples of transverse waves: light. All electromagnetic radiation are transverse waves. Waves in a rope. You know, if you were to wiggle a rope, it makes the rope go up and down, but the wave goes side to side. Water waves are mostly transverse. S waves in an earthquake. They're called S waves. They're transverse. It sends out a transverse wave from an earthquake. And how many of you have done the wave in a sporting event? You know, we could do it now, but you guys look. You want to? You guys stand up, or just do your hands, right? And okay, we'll start over here. Go. And back. And go. And back. That's a transverse wave. You, the individuals, the medium that it transmits, you're the vibration. You just go up and down. But the wave, the disturbance, is going side to side. That's a transverse wave. Longitudinal, sound waves. Me talking makes the air in the room look like the slinky. It compresses and spreads out and wiggles like this. Hello, Spencer. And it goes like, makes the air go like this in the direction it's traveling. Pressure waves are longitudinal. And an earthquake puts out a longitudinal wave too. They're called P waves. So it puts out two types of earthquakes. S waves that are transverse and P waves that are longitudinal. So they travel through the ground differently. Yeah?
Do you measure wavelengths the same way?
I'm glad you asked. Do you measure the wavelength the same way? Yes. You know, this is hard for me to draw, so I found something online. I'll show you. Oh, of course it turned off. The distance, while that's coming up, when the coils compress, we call it a compression. Makes sense. When they spread back out, they're farther apart, less dense. We call that a rarefaction. 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 It's in your text. But that means like the air is rarefied, if you've ever heard of that. It means there's less of it. It's thinner. It's less dense. So you get compressions and rarefactions. Compressions, rarefactions. I like to call it squishing and spreading. Squishing and spreading. And maybe this is still on video. That could be why. So here's an example of it moving. You would say the distance between compressions or rarefactions is a wavelength. So I know it's moving, but from, see the compression here, and then it's a compression. It's squished and then spread apart. Squished and then spread apart. Squished and then spread apart. The individual particles. So the distance from one of those compressions to the next would be a wavelength, kind of like a crest to a crest. And the rarefactions, the spreading out to the next one, like a trough to the trough. But it vibrates with a certain period, certain frequency, and you can see the pulse traveling across the screen. Like this compression seems to be moving with my laser pointer. I'll start over. That's the wave, and I'm going at the wave speed. All waves, all types of waves and kinds, all this stuff applies to frequency, wave speed, period. But that's what the air is doing when I talk. If I try to sing one only note, Ooh. Then the air is doing that. Yeah, Brian. It looks like it's rotating to me too. It's an illusion though. Try to follow just one spot. Try to focus, that's the hard part, on one. And you can see it, all it does is vibrate left and right. Convince yourself. Pick a second spot and follow it. The medium doesn't propagate. It just vibrates. The pulse, or the wave, is what propagates. All right, we're used to dealing with matter, substance, usually solid things. And matter doesn't like sharing space with its friends. I don't see any of you sitting on top of each other. We don't like sharing the same space. My mother-in-law has a pretty big bubble space. If you ever watch this, Louise, I'm sorry, but you do. She knows it. Everybody has their own little personal bubble space, but we don't like to share space. Waves can. They can share the same space. So if you have a wave coming at you like that, and you have a second wave that looks the same, if they overlap or come together in this either direction, this way or this one overruns, if they're in the same space at the same time, they simply just add up. They're displacements, that vibration displacement. And so those would look like, this one's trying to vibrate it up, and so's that one at that time and space. And so it's like you get a double kick, drawn roughly to scale. This is called constructive interference. Constructive interference, because in English constructive means good, positive. They reinforce each other. We'd also say these two waves are in phase. I briefly did a demonstration on the overhead last time where I turned a crank. You go in a circle. You can start at 0 degrees and go around 360 degrees. If one of these waves, so to speak, is like at 0 while the other's at 90, we'd say they're out of phase. I'll draw that next. These are in phase because they're both up at the same time. They're both down at the same time. That's why we say they're in phase. And they superimpose, I'll get to your question, superimpose. Well, let me write superposition. It's more generic. This adding up of waves in the same space is called superposition. And this is a specific example where they constructively interfere. Okay, there were some questions.
Is that kind of like resonance?
Yes. Yes, this would be resonance. If these two crossed each other for that moment, yeah, they're, yes.
If you took like a guitar and you played like a D note, and then you played a D an octave higher, do they press and stuff the same, or just different?
That's a great question. If you played a D on the guitar, let's say it looks like, I don't know, this. Because it has a certain wavelength and frequency. If you now play a D an octave higher, we haven't gotten there yet, but we can discuss it. How do you think its frequency will be different?
Touch the line in the same spots, it just doesn't press and stuff.
Yes. Yes. I'll repeat that. Let's say, for convenience, it starts here. Well, let me draw it down here first. It would vibrate faster because it's higher. We know it's a higher pitch. We make the connection. That means it's vibrating faster. If something's vibrating faster, that means the periods are shorter. the sound is traveling through the wire in either case. So the speed it travels is based on the medium it's traveling through. And so we're not changing the wave speed. You got that? It's the same string. So when we change the frequency by doubling it, that's actually how much it goes. It doubles for an octave. It's twice as fast. Then the wavelength must become half as long. So there's shorter waves. If I can try to draw that, let's see. So instead of peaking when it does, it'll peak like this. The wavelength is half the distance. It goes up and down twice as fast. And then these superimpose on top of each other, superposition. And at some points they add up, and some points they don't. See, here it's up, and this is sort of up. So you might get, you'll get an up. This one's still up here, but it's down here, isn't it? There, they're going to kind of cancel each other out. And you'll come back down to a 0 point. And then this one's up while that one's down, and so it's canceled again. And this isn't perfect because I can't do it in my head, but you're going to get something like, not a perfect sine wave. And that's called superposition, the adding of two waves. So they're not always in phase. Sometimes they're out of phase. And you might see this waveform. We're going to see some of these later. Not today. And that tells us, ooh, there must be more than one frequency going on there. So ideally, cleanly, if this one's up, when this one's down, what will happen? Right, it looks like that. There's no displacement. If these are perfectly identical and perfectly out of phase, then when that one's up, this one's trying to make it go down. They cancel each other out, and you get no movement there. We call this destructive interference. Destructive interference, they're out of phase. You can, of course, have everything in between. They can be partially constructive, somewhat destructive. If this one has a much bigger amplitude, like this, then when these two line up, they still destructively interfere, but not completely, because this guy's trying to move it down more than this one moves it up. So you might get less of a vibration, but it's not completely destroyed. So if this were sound, it would be quieter, because the amplitude is less. It's like turning the volume down. We can do that on here. Hopefully. Let's see if I can. So I'm going to send a pulse up, make a crest, and make it go that way. Let's see. And it reflects, comes back. This time, I'll try to make a pulse up on both ends and have them come together. You guys want to watch what happens in the middle when they superimpose and interfere with each other. What do you expect to happen if this one's up and this one's up? Twice. It should be higher. Constructive interference. Okay. Whoop. Oh, yeah, so much it hit the table. Maybe I will use less amplitude. Whoop. So you get bigger, and again, whoop. Whoop. That's constructive. Now I'll try to do the destructive. One up, one down. Vroom. Again. They just seem to pass by each other. Waves can take up the same space. They do. They just kind of pass through each other. Watch the bump. Try to follow one bump. It reflects. You can watch it again. But for that brief moment in the middle, you get no movement when they were the same. That's interference. And that can work with longitudinal waves as well. I'm just not as proficient, so I can't show you. I want to show that a different way. Again, this works for all waves. We're going to cover light after this unit, after the test on all this. We'll cover light. Light's a wave, and all this applies. Bless you. So the idea is, let's go this way. We'll go down. So this point, you can think of as your sound source. How about a speaker? And the cone vibrates towards you and then recoils back. Towards you, back. Towards you, back. So it compresses the air in front when it goes forward, but when it moves back, it rarefies the air, spreads it out. So these wave fronts, think of these as wave fronts of compressions, if you will. Here's a second speaker that looks the same. If you shift the two speakers so they come from different spots, they overlap and they interfere. So here, can you see a darker region? And another one here? And over here? We could say that's where the crests line up and it constructively interferes. So if you were sitting right here, you could hear the sound louder than if you were sitting right here. Because that's where when one crest is up, the other's down. Well, you can consider the dark spots crest or the light spots crest. You get the idea. One of these regions, you get constructive interference, and in the other, you get destructive. How many of you have been in a room and you move a little and it's like a dead spot? It's because that's what the waves are doing. They're interfering. The wave from the one on the right has to travel a slightly different distance compared to the one on the left. And when they overlap over here, they might be in phase, they might not. They travel different distances to this point. And so they could be in phase there and not there. You with me?
Well, is that why home theaters are really tricky to set up?
That is why home theaters are very tricky to set up. And this is with two identical frequencies on an overhead projector. In a room, what else happens? You have multiple frequencies at the same time, so they'd never perfectly cancel out or add together. And you got furniture absorbing frequencies and walls reflecting frequencies. You get echoes, reverberations, and taking all that into account is the field of acoustics. And yeah, to do it right exactly the way you want can get complicated. You can see you get more interference happening in a smaller region if you space them out farther. And since I have this up there, we'll revisit it, but this is true with light. If these were light sources, two different lasers, or you sent a laser through two different openings, so like they came from two different spots, the same light, they interfere like this too, and you can see the pattern on the wall. I'll show you that later. That's called interference, just like these waves. Sound is a vibration that travels through air. Yes? 5 minutes. 5 minutes. I think I can do it. I won't ask you clicker questions. I want to show you this. The Doppler effect is what I'll end with. A lot of you have heard of it, so I don't think it'll take that long to demonstrate it, and then we'll review it again next time. The Doppler effect is a phenomena where waves interfere. But because the source, this is a buzzer, or the receiver, your ear, are moving with respect to each other. So I turn this on. Sorry, Brian. And then I spin it. I need to come up front. This isn't pleasant, but when I spin it around, you should hear a kind of a wah-wah. It seems to change frequencies. This isn't changing. This is still putting out the same frequency the whole time. That. It's actually a couple frequencies. You can tell because it doesn't sound good. But they're not changing. So why does it sound different to you, like it is changing? Yeah. As I whip this around and it's coming, while it's coming at you, you should hear a higher frequency. And when it's coming away, going away from you, you should hear a lower frequency. Let me do it again. I'll draw cooler pictures showing this next time. But if you spin anything at a certain frequency, you can hear that wah-wah, and that's the Doppler effect. The waves are superimposing in a way that you think it's different. These are called bluegills you can get at a toy store. Do you hear it kind of wah, 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 wah? That's because it's rotating. I can spin this faster, increase the frequency, but you should still hear a change in that frequency, a wah-wah. Do you still hear it? Wah, 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 wah. Here's another version. You're okay. This has a reed in this side, like a clarinet, and when the wind blows past it, it vibrates at one frequency. But as it comes towards you versus away from you, you hear something different. Here's a buzzer and a ball. There's the frequency. Okay, catch. Let me come up front. Over there. Can you hear it shift? As it comes at you, it should sound higher frequency. How about all the way in the back? That was good. You up for it? No, you. Could you hear it? Sorry, Brian. All right. That's the Doppler effect. There's good pictures in your book, and I'll show you some more next time, but it's just waves interfering with each other. See ya.